Okay, so Jacob had a question about the proof of essentially um, essentially this is what we use to solve exact equations, right? So this is saying that if I have a function f of x and y equals c, and I can supply that function f so that it has an x derivative here and a y derivative here that satisfy this differential equation, then this thing actually works as a solution. You guys kind of with me on that? So the way I'm going to use this in practice is I'm going to have a differential equation that looks like m dx plus n dy is 0. And I'm going to kind of look at this and I'm going to think, hey, what if that thing's fx? What if this thing's fy? If I can find a function f with that property, then I can say, okay, so then f of x and y equals c is the whole family of solutions here, and I can just kind of be done. You guys all on board with that idea at least? Okay, and then I just need to kind of I'm trying to analyze this and check basically that this, I don't know, satisfies this differential equation, really, right? I've got a function. I want to check that this thing actually works for it. And so, all right, we're just trying to read through the book and parse out what the hell they're saying, right? So they say, okay, so if y is a function of x and we differentiate implicitly with respect to x, so my kind of thought on that is I'm thinking, all right, so they're saying I've got this equation, f of x and y is c, right? I don't know that x is a function of y. I don't know that y is a function of x. You guys see that? I'm going to pretend for a minute that it is. So I'm going to suppose that at least locally, y is a function of x. That's what this kind of first thing says. So this first thing is kind of thinking y is a function of x. So then if I take my kind of overriding equation that I'm looking at, I'm going to call this guy star. Okay. So I'm thinking I'm going to take star, right? And I'm going to think about it as f of x and y of x. You guys all with me on that? Okay, now this is the part where calculus comes into play. I want to check that this thing satisfies a differential equation, right? So what I'm going to do with it is I'm going to take this thing, I'm going to hit this sucker with a derivative with respect to x. You guys see that? Okay. Now, the kick is here that f is a function of two variables, right? So if I kind of go back to the Calc 3 chain rule, I've got f is a function of x and y, and I'm thinking y is a function of x. You guys with me on that chain rule? Okay, so, I guess I should denote x is also a function of x, right? Just to have everything, just to have my tree to the usual levels. So the Calc 3 chain rule says that when I hit this thing with the derivative, I better believe I'm going to get 0 on the right-hand side at least. Because everybody's on board with the derivative of a constant with respect to 0 is going to be 0. Now, on the left-hand side, I need to write down the whole chain rule. So that's going to be the partial of f with respect to x, right? That's this branch here, times the derivative of that function with respect to x. Then going down, so that's this branch, right? Now going down the other branch, I need the partial of f with respect to y. And then y only depends on that one variable x. So I have a times dy dx here. That makes sense, Jacob?
Yeah, that pretty much answers my question.
Yeah, I thought it might. It's a little bit weird. It feels like, hey, dude, they did a product rule here. Like, what the hell?
Yeah.
But, like, it's not the product rule, right? So, like, where the hell did it come from?
I was mainly wondering because since they say they differentiate with respect to x, I was like, why do they have the partial derivative of y then?
Yep, exactly. Yeah, it's a super weird application because we don't usually think about that tree as being like, oh, well, it's one short branch over here and it's a long branch down there.
Oh, well, I wasn't even thinking chain rule. I don't know why I wasn't thinking calc 3 at all for this, but
It's okay. It's one of this is the only spot where we talk about Calc 3 in the class, so it's a little bit strange to be like, "Hey guys, remember the chain? Remember the ultra specific thing about the chain rule in Calc 3?" So in the end here, right? We've got this is fx of x and y, and then we have times 1, and then we've got fy of x and y, and then times dy dx is 0. And then we can see that, well, if we multiply both sides here by dx, we get fx dx plus fy dy is 0. And then, they spend a second more talking about this, and it's not that the probably is worth reading, really. But really, it amounts to, hey, if you do this the other way, it still works. And those are really the interpretations. And there's a there's a little bit of weirdness here because you'd want to say like, but dude, what if it's not a function of either one? Like, what if you can't think about y as being a function of x, or you can't think about x as being a function of y? Like, what if just both don't work? And that kind of comes down to some assumptions and some well, frankly, some harder shit. Like if you want to deep dive that one, you're gonna want a real analysis class in a master's program. To
I
be
was
honest.
gonna say this class, or at least this textbook, has done a lot of we'll say this without proof because it's beyond the scope of this textbook.
Yeah, we've really like this class is one of those areas where in order to get to in order to get from what we're looking at in the textbook back to sheep, we have to take an up and around path, which doesn't happen very often in the kind of beginning mathematics courses. Like most of this stuff from calculus, like you can take it from where it is and you can pull it straight back to sheep, and it all makes sense. This is we're kind of starting to reach that like partial fraction decomposition idea, where we have to head up a couple of levels to find the explanations for these things. So I mean, we've also lied to you a lot, which makes it like we're starting to lie to you less. And so it's starting to become more like, yeah, the proof for this is actually really hard, and I'm not gonna pretend to show you one that doesn't work. Whereas in calculus class, I'll show you some proofs that don't work, and you just won't notice because you don't like you're not that skeptical yet. But now you guys are getting kind of smart, and it's harder to hide things from you. So I'm gonna stop. Does that sort of answer that?
Yeah, it's not what I expected, but yeah, it answered my question.
Do you want to know all the things you've been lied about too, or lied about? Do you want to know all the things that we've lied to you about?
Yeah.
It's all of them.
Aw.
So the thing is, I had a professor who used to describe this as it's not that we ever actually lied to you. The things we tell you are morally correct, but they're not actually correct. They're just mostly correct. So he used this word morally a lot. Like it's kind of a moral dilemma as to whether to drag you way down in the weeds or show you that you can use math for something. So we tend to err on the side of like, let's show you that you can use math for something, even though most of the presentation's a little flawed.
Joe, are you of the feeling that math is invented or discovered?
Um, I'm gonna. I kind of come down on that question as it's a bit of both. Um, the I think the things that we value most in math are discovered, but I think a lot of stuff gets invented in order to kind of pursue the things that we discover. Does that sort of make sense? And you can always tell when something's just right. It clicks and it's super elegant and everything is easy to understand, and that's the moments when you know math is discovered. Unfortunately, not all math is discovered. We made some stuff up as we went along. And so there's some things that were invented that are really awkward to deal with. And I tend to be a believer that like like exactness feels discovered because it's so fucking slick. Whereas other things like oh, I don't know, like homogeneous nonlinear equations, they feel kind of invented. Like they're sort of a shit trick. It's not something like. They just don't feel as clean, you know. So, yeah, I don't know. Like Euler's identity feels super discovered. On the other hand, like Taylor polynomials feel pretty invented, and you kind of need them to see Euler's identity. So, I don't know.